So you need to realize that your random variable may be normally distributed even if the sample fails the 3 tests. Because again, if the sample's too small, we might not be seeing a representative group of what the population distribution really looks like. However, if the histogram definitely doesn't look symmetric and bell-shaped, there are outliers that are very extreme, and the normal probability plot doesn't look anything like linear, then you can probably be fairly confident that the sample data set does not come from a population that's normally distributed. And again, we're saying fairly confident. We're not making a fact statement because, again, here we are making inferences. So they are just educated guesses. We're not just stating facts anymore. We're taking the sample data and we're trying to make a reasonable conclusion about the population. All right, so in the next examples, you should upload the file called Chapter 6 data file into StatCrunch, because we're going to, and again, those data sets, these are pretty big data sets that are already built in there versus typing all of those data points into a list in your calculator. So for this next example, there is a list of data called time between eruptions that has these 64 data points already typed in. So example 6.4.1, is it normal? And again, when we're talking normal in statistics, we're not talking normal versus abnormal. We're talking about a very specific shape distribution, normal distribution. All right, so in Australia, there is a blowhole, and the data in table 6.4.1 are the times and seconds between eruptions. So do the data come from a population that is normally distributed? So again, we're going to start by stating our random variable here. And again, for quantitative data, we're going to be looking at the measurement of a randomly selected object. So in this case, we're going to look at the time in seconds between eruptions for this. So in this case, we would be taking like 2 randomly selected eruptions, consecutive eruptions, and we're looking at the time space between those. Okay. All right, so again, we want to know if it's reasonable to assume that the data came from a normal distribution. So we're going to make a histogram and look at its shape. We're going to look at a modified box plot to check for outliers, and we're going to make this new plot called a normal probability plot to see if that looks roughly linear. So to check if data come from a normal distribution, those are the 3 graphs that we're going to be making. So the first step here on part B is to draw a histogram. So again, if we actually took the time to type all that data into the TI-84 and made the histogram, again, we're just using Zoom 9 here, letting the calculator automatically choose a bin width and where to start the bins at, and then it automatically adjusts the Y min and Y max to fit all of, and X min, X max to fit all of the data in screen there. Or again, if we go into StatCrunch and pick from the list of graphs, picking histogram, and again, we're not entering a bin width and we're not entering a value for where to start the bins at, we're just hitting compute. Just to let it automatically pick those. So again, if we notice that these 2 graphs are slightly different because the calculator is picking a slightly different bin width than StatCrunch is, but either way, even though they don't look exactly the same, both of them have the same basic shape, which is a right skewed graph. So notice that the TI-84 and StatCrunch use different bin widths when you let them choose the bin width automatically. The histograms do not look exactly the same, but both histograms look right skewed. And definitely are not bell-shaped. And not symmetric. So part C, if we go ahead and check for outliers, again, if we had taken the time to type in the big data set into the calculator, again, using Zoom 9 to get our modified box plot, again, we can push trace to arrow over to see, again, these are outliers, which means they're values that are beyond, in this case, beyond the upper fence. We have high outliers in this case. And if we trace over those, we see that this one, as we trace over it, the calculator tells us that that's at 146. And this one, as we trace over it, tells us that that one is at 169. So the data points at 146 seconds and 169 seconds are outliers for this particular set of data. And again, we can see those two outliers here when we make the modified box plot using StatCrunch as well. Now you can also find the outliers using the fences instead, but again, it is just faster to use the graph. But this method still works that we had looked at back in the first unit as well. So this lower fence, we take Q1 and subtract 1.5 times the IQR. And so in this case, our lower fence, see, our lowest data point was 14.5, and then we would subtract 68.25 because that's what we computed here for 1.5 times the IQR. Okay. And our quartile 1, we can get that off of our one variable stat screen to get that at 14.5. And so if we subtract those values, we get negative 53.75 seconds. Okay, so obviously we're not going to have anything below the lower fence because we can't have negative times. Now the upper fence, we would take Q3, which was 60. Let's write our formula here. So we're taking Q3 plus 1.5 times the IQR. So the third quartile was 60, and we're adding 1.5 IQRs, which we've already actually computed that. So 1.5 IQRs was a 68.25. So if we add those, we get 128.25 seconds. So outliers are any numbers that are greater than 128.25 seconds or less than negative 53.7 seconds. All right, all the numbers are measurements of time, so no data values are going to be less than 0. So obviously nothing less than negative 53.75 seconds. But there were two numbers that were larger than the 128.25, namely the 146 and 169 that we found on the graph. Again, fences still work, but faster to use the modified box plot. All right, so the last step here is the new graph, so drawing the normal probability plot. So again, if we had entered this data into the TI-84 and used the 6th plot, so again, remember this is the 6th plot on that screen to get a normal probability plot for the data. Okay, and we see that this does not look very linear. It's kind of got a big hump here, and we see the two outliers over here that kind of stray away from the pattern as well. But again, a little bit easier to look at on the QQ plot on StatCrunch because it actually plots the line that these values should be approaching. And so we can see that, you know, we've got all of these values that aren't anywhere near the red line, and then we've got this kind of hump of things above the line here, and then these kind of stragglers way over here. So again, looking on our graph here, we can say here that the normal probability plot is not roughly linear. Okay. There's a lot of curvature. Okay, so we're not looking for picture perfect dot to dot linear, but in here there's a lot of curvature, and the points deviate far from the line displayed. All right, so putting all those pieces together to answer the question, is it reasonable to assume that the sample data came from a population that's normally distributed, we would say, considering that the histogram was skewed right, so not bell-shaped, and there are two extreme outliers, And the normal probability plot does not look linear. So it kind of violates all three of the things that we were looking for. We were looking for bell-shaped, we were wanting no outliers, and we were wanting the normal probability plot to look roughly linear. And none of those things were true. All right, so the conclusion is that this sample, the conclusion is that it is not reasonable to assume the sample came from a normal population. Again, that's our educated guess. So it could be that this data actually did come from a normal population, but based on the evidence we've seen in these three graphs, we think it's highly unlikely to have come from a normal population.